review where we got to in the first lecture. So what we derived there were a system or set of balance equations. Balance equation for mass, linear momentum, and the energy of the velocity fluctuations. So T is the strength of the velocity fluctuations, and the structure of these equations is likely to be familiar to you from your studies of the mechanics of gases or liquids. The only unusual term here is the rate of energy dissipation due to the fact that collisions between particles are inelastic. They inevitably dissipate energy. And the interesting feature that gives to the energy equation is that the energy equation in this situation for this material can have steady solutions. So unlike the energy equation for a molecular gas, in a homogeneous situation when this term is absent, because of the presence of this term, there can be a balance between these last two terms, the production of fluctuations essentially by the mean gradients in the mean motion, and its dissipation by collision. So the idea is that in the simplest possible shearing flow, we have the possibility of collisions being driven by only the difference in the average velocity of the centers of two spheres associated with their positions, and this collision will create velocity fluctuations, deviations from the mean, but at the same time there's also an energy loss in that collision, and under appropriate circumstances there can be a balance of these two contributions to the energy equation, and the energy equation can be satisfied in a steady situation, and then that determines the quantity T, the strength of the velocity fluctuations. And also for this particular gas of colliding particles, the internal energy is extremely simple. It's just related to the kinetic energy of the velocity fluctuations of the spheres. Okay, so those are the balance equations. They're not too mysterious. This typically is an external force that's due to gravity in most of our simulations. And in the first lecture, we derived not only the balance equations, but we derived expressions for the transport of linear momentum and fluctuation energy, and an expression for the rate of dissipation of fluctuation energy. And those constitutive relations had this structure. This is a typical thermodynamic pressure. This quantity kappa is a product of the density, a known function of volume fraction. Sigma is the diameter of the particle, and this is the strength of the velocity fluctuations divided by pi. Here is the relationship between this function g, a function g0 that has the significance of being the value of the radial distribution function for a pair of colliding spheres, and in numerical simulations that dependence of this function g0 on the volume fraction can be measured. So that's the way we get that. It's not predicted from first principles. It's measured in numerical simulations of colliding spheres. And in a particular situation when the colliding spheres are colliding elastically. And then there's no energy being dissipated in that system. You can set it. You can set off the colliding system at a given temperature and at various volume fractions and measure all the properties that you like in that particular system. So that's where we get a function like this. And I'll be saying something more about this numerical coefficient in a moment. 0.64 is the volume fraction for random close packings of spheres. So that's the physical significance of that number. Here, d is simply the velocity, the symmetric part of the gradients, spatial gradients in mean velocity, and the structure of the pressure tensor, which is an opposite of sign from the stress tensor, is that there is a, if you like, a thermodynamic contribution that's independent of the shear rate, a quantity that's associated with viscous resistance to changes, to rates of change of volume that you may not be accustomed to because it's usually assumed to be absent in Navier-Stokes equations for liquids and gases. And then finally a resistance to shearing, typically. I mean, this also has an isotropic component that contributes to these unit tensors, but this contains the resistance to shearing. And in this particular simple theory, the coefficients that appear in both the pressure, thermodynamic pressure, and in the viscous resistance are the same. Now, as I say here, the unknowns that we're dealing with this set of equations are the mass density, the three components of the average velocity of the gas, and the measure of the energy of the velocity fluctuations. And these appear in the transport coefficients. And in particular, you see the temperature, T, is appearing prominently almost everywhere we look. So that's why we have to carry this equation for the energy of the velocity fluctuations. Okay, so that's the story of the pressure tensor. It's a similar situation for the flux of fluctuation energy. That has the form that was first put forward by Fourier for conduction of energy, and the thermal conductivity coefficient is proportional to the viscosity in this simple case. Now remember, in the derivation of the constitutive equations, we made certain simplifying assumptions for something called the complete pair distribution function, relating that to the product of the single particle velocity distribution functions, and then we assumed that those single particle velocity distribution functions were Maxwellian. So this is really a very simple theory. But it's rather more transparent to derive it. That's really the advantage of this theory. And it applies only to dense situations. So I would say flows greater than 30% concentration. Okay, and finally there's the rate of collisional dissipation. It involves also this coefficient kappa, but and the coefficient of restitution, the number E, that measures the amount of dissipation in a collision between two spheres. And of course, we can measure the coefficient of restitution by studying a collision between two spheres of our interest. Okay, and it's not a very difficult experiment to do. So you can regard this either as a phenomenological parameter or as a parameter that can be measured in advance of any experimentation or numerical simulations. Okay, so that's the story. We have a system of 4 equations, given that u is a vector. I'm sorry, a system of 5 equations, given that u is a vector, and those equations are closed by the constitutive relations. So in fact, it seems as if we can phrase and solve problems in order to test the theory. Okay, so that's what we're going to do in this lecture. We're going to phrase a boundary value problem for an inclined flow and see how the theory produces solutions for the fields of interest. Okay, but before I do that, I want to say a couple things here. Let's see. So I want to talk a little bit about this object here. And in particular, I want to say where this number comes from. So this quantity G0 is called the contact radial distribution function. And in effect, I wasn't extremely precise, or perhaps extremely correct, in what I said about it in the first lecture. That is, in the range of volume fractions between 30% and 49%, this has a somewhat different structure than what I wrote down. And this is a structure that is determined, again, in numerical simulations of equilibrated cloud of colliding elastic spheres. And this is a form that is due to Carnahan and Starling. They did these kinds of experiments in order to determine this function. So it's a measured function, fit rather well by this function of solid volume fraction. But it turns out that for volume fraction, so this is singular at unity, okay? But we've already said that in fact the singularity should be occurring at a volume fraction of 0.64 because that's where random close packing is. So this function works pretty well as long as you're away from 0.64. But if you want to approach random close packing, then you need to have another form of the function, and this has also been determined in numerical simulations. So this is due to Torquato, who carried out the simulations and did the fitting, and it results from trying to get a smooth transition from this function to a function that is singular at 0.64. So the value of this second function is G0 evaluated at 0.49, and then this ratio 0.64 minus 0.49, that is this ratio that is equal to unity at 0.49. So that gives us a smooth transition between this function and when we evaluate the numbers that are involved here, that is when we evaluate this function at 0.49 and multiply the result by 0.64 minus 0.49, you get this factor of 0.85. So that's where that factor comes from. It's not just pulled from the air. It's a factor that ensures that two versions of this contact radial distribution function, one at a lower range of volume fraction than the other, meet continuously at a point. Okay, so that's one thing I wanted to say about that. And also, so notice that this range, or this radial distribution function, is the one that really is working in the range in which I was saying I wanted the theory that I just derived to be limited. Okay, there's a problem, as we'll see. That is, we've derived this simple theory, and the question is, over what range of volume fractions does it work? Okay, and I'll tell you in advance that we're going to see that it works up to a volume fraction of about 0.49, and beyond that, it fails. Okay, so in fact, by using this volume fraction in the theory, let's see. Yeah, so I'm proposing that we use that volume fraction in the theory, and the reason is that I'd like to try to push this theory beyond a volume fraction of 0.49 in order to see whether or not it fails. Okay, and it turns out that over the range of between 0.3 and 0.5, these two functions are about the same. Okay, so it doesn't make too much difference that I'm using over the range 0.3 to 0.49 an expression for this function that is really not entirely appropriate because it doesn't differ by too much from the function that is. Okay, so I'm apologizing for using a function that is not exactly the one that I should be using. Okay, all right. So there's one more issue that has to be made, or at least addressed, I think, and that is what's so special about the volume fraction 0.49? Why am I making all of this fuss about distinguishing range 0.30, 0.49, 0.49, 0.64? Okay, and here's the story, is that I'm using a figure from another source. So here's a ratio of pressure to the thermodynamic pressure divided by the mass density of the material of the spheres and the temperature. So this is just a function of nu. It's 4 times this 4 times nu times the capital G function that I've talked about. And it has this character. It's not monotonic. And everything I'm saying is true exactly for a gas of identical elastic spheres. Okay? So what this is saying is that a gas of identical elastic spheres, and by a rough projection, our gas of inelastic spheres, is capable of exhibiting a phase change. That is, for a given system, as we increase the volume fraction in our box, let's say, of colliding grains, we come to a value of this ratio in which there is more than one solution possible. Okay? And that value at which of the volume fraction at which there is first more than one solution possible is 0.49. So the idea is above 0.49 there are two states of this colliding gas of particles. One of the states, the spatial distribution of particles, is random. In the other state, the spatial distribution of the centers of these particles is ordered. Okay, so in the second state, it's an ordered arrangement of particles. They're not in contact; they're in collisional interaction, but it's ordered. And so the point is, from beyond this volume fraction, we're dealing with the possibility of two states, and typically in a numerical simulation, well, I should say, it's the possibility of three states. One of these states is unstable, so we don't see it in the numerical simulations. But two states are possible, and for volume fractions above 0.49, typically you get a mixture of two states. And then, as you attempt to exceed this volume fraction, there's slightly less than 0.64, there's only one possibility, and that's the ordered state. So you experience from 0.49 up to this volume fraction a mixture of random, typically a mixture in random and ordered colliding states, kind of a polycrystalline gas. And then above this, in principle, if you achieved the state of lowest free energy, you're in this ordered state. Okay, so that's the significance of 0.49 in terms of a volume fraction. Now it turns out that the state cannot, you need not have the system get into the lowest state, partially or completely. That is, it might find it difficult to do that. And consequently, there's the possibility that you continue to go up a random branch to which has a limiting value of 6.4. The limiting value of the ordered branch is 0.74. That's hexagonal close pack. Okay? And typically, the granular systems are staying on the random branch. Okay, it's the random branch then that is whose volume fraction dependence is described by this 0.85, 0.64 minus nu. Okay, so this, I mean, it may be surprising that there's a phase change that's possible in this simple collisional system, but it's well observed and rather well documented. And the interesting thing about it is it doesn't take place because of attractive forces between the spheres. There are no attractive forces. This is a phase transition that's driven by entropy. That is, the ordered state above some volume fraction is more likely than the disordered state. Okay, so that's all by way of describing why this number 0.49 enters into anything that I say.
I have a quick question.
Yeah.
Your horizontal axis is volume fraction only, right? So
Yes.
and you have two possible states that we see. Is it likelier that the one on the left is seen more often when the level of agitation is higher?
No, it's independent. It depends only on volume fraction for the simple system that I'm talking about. Okay, and exactly. I mean, this is for an elastic system of spheres. Of course, we're dealing with an inelastic system of sheared spheres. So that's another issue that influences the volume fraction. I mean, it influences the phase change. That is, having shearing the system may be suppressing the phase change. And it does, in fact. But the vestige of the phase change, as we'll see, contributes to ordering in the system. And that ordering this in the system is destroying the assumption of molecular chaos that we built our constitutive relations on. Okay, so that's what's happening.
So how do you get this picture? From simulations?
Yeah, from simulations.
And so they are measuring pressure directly from the simulations?
Yes. Yeah. So that's the first simulation that discovered this phase change was done by Adler and Wainwright in the late 50s, I think. And it was a surprise.
So the unstable part, how do you get that? That's from theory.
You don't get the unstable part because you don't see it. But it's this kind of a curve is characteristic of the first order phase changes.
I had one more.
I mean, a van der Waals gas has a, yeah.
Is there a simple way to picturize the radial distribution function in terms of what is it?
Well, so a way you measure it, so you focus it, so you have a gas of thousands of spheres interacting, and at any time you take, let's say you freeze the picture, and you characterize the likelihood of particles residing in a narrow ring about the central particle, and you plot that. Okay, so that let's say this is the diameter of the particle. So we start from, let's say, r over d. Okay, so there's no particles, no centers of particles possible at a distance less than a diameter, but as it turns out, there's a exceptionally increased number of particles close to there, and the function typically goes like this. Let's see. So this is G0 as a function of r. Let me write it this way. G0 as a function of r, and that's parameterized by nu. Okay, so that the equilibrium value at great distances is a function of nu. And the value we're interested in is this value right here. the value of the radial distribution function for contacting particles. Okay, but this is the way you measure it. So it's, if you like, it's a,
The number of particles or the, how?
yeah, so like either the number or the likelihood, depending on whether you're normalizing by particle number or not. Okay.
So the origin is actually 1 plus some.
1.
Okay, 1.
Okay. All right, so that just was the recap. Okay, so here we are. So now what I want to do, as I mentioned earlier, we want to phrase and solve boundary value problems for flows above either a rigid bumpy boundary. So I drew something. So I'm going to be looking at incline flows, and we're going to be looking at incline flows over boundaries to which spheres have been glued. That's what I mean by a rigid bumpy boundary. So above them we have a dense gas of colliding particles, but the colliding particles are colliding also with the boundary. Okay? That's fine. And another problem that often occurs is when we don't have a rigid bumpy boundary, but we have a flow of particles, an incline flow again, over a bed of particles. Okay, and that's another situation that we'd like to study. And of course, in order to phrase boundary value problems, we've got to have boundary conditions. Okay, so that's going to be part of the activity. But now we're experts at deriving constitutive equations for colliding grains, so deriving the associated boundary conditions shouldn't be any problem. Okay, so that's what we're doing. All right, so first let's go back to our constitutive relations. But now here, I answered a question that I think came up in the earlier lecture, and that is, how do these relations that we derived without really making any appeal to Boltzmann equation or the derivation of the single particle velocity distribution function, how do these constitutive equations relate to the ones that make use of this apparatus to generate the constitutive relation? And here I attempted to provide the answer. So these have the same structure, although I've written them in a different way here, but they have the same structure as the constitutive relations that we just saw earlier. But if in the crude derivation, this quantity J that appears in the shear viscosity is unity, while in the detailed derivation, solving the Boltzmann equation using the Chapman-Enskog procedure, it is 1 plus pi over 12. Okay, so we're making an error of 25% in that instance. Okay, the situation is a little more dire with respect to the thermal conductivity. In that case, we have a function that I call m here, and m is unity in our crude derivation, while in the more sophisticated derivation, it's 1 plus 9 pi over 32. So there, it's really maybe a factor of 2 that we've made an error in. Okay?
So when you say crude, you mean you're using the Maxwell distribution?
Using, yeah, everything I did last lecture, using just the Maxwell distribution, the assumption of molecular chaos, and the only reason we were getting coefficients is we did a Taylor series of the single particle velocity distribution function. So we had, I didn't mention the Boltzmann equation at all.
And when you say doing the Chapman-Enskog procedure, you're using the correction to the distribution function?
Yes, we're deriving, it is really derived as a correction to the Maxwellian distribution functions. Yeah, using this Chapman-Enskog procedure.
Up till what order?
All linear.
All in.
Yeah, all linear in the spatial gradients. Okay, so that's, so, you know, so the answer is qualitatively we have a good theory. It's got all the structure of the more refined theory. Quantitatively, I mean, we're not doing badly. We're not off by orders of magnitude, but there is a difference. Okay. So that's that. So this is the theory that I'll be exercising. That I'll use these coefficients J and M. And I should say, so I'm still focused on nearly elastic spheres. That is E, the coefficient of restitution, near 1. Okay? Now, when the coefficient of restitution is away from 1, then this Chapman-Enskog procedure provides you also with the way, for example, these coefficients depend upon the coefficient of restitution and also volume fraction, if you want to take that into account explicitly. Okay, so the Chapman-Enskog procedure gets you a lot more detailed information. But we're going to be happy with this. Although, let's say maybe in the next lecture I give, I'll introduce values of J and M for the more dissipative systems, more dissipative dense systems, I would say.
So here the correction is due to only, it's not order E. The correction is due to the pi by 12 and the 9 pi by 32 are coming due to size effect.
You mean not?
So the correction to the Maxwellian distribution is driven both by the dissipativeness
Yes?
and by the size. And this correction is only due to the size of the sphere, is it?
I don't know that I can agree with that because the size doesn't appear in the correction.
So then when you expand the distribution, it is F0 plus the Knudsen number, I believe, which is this size.
Yeah, I mean, your fundamental question is why? Well, the answer to your question is that the single particle velocity distribution is not Maxwellian because the Maxwellian is for the equilibrium situation. So there are deviations from the Maxwellian that are due to the existence of spatial gradients. So it's the existence of spatial gradients in the problem that drives the Maxwellian away from being the single.
I was just wondering when, so the way, as you said, would be to expand the actual distribution function about the Maxwellian, and the corrections will be order of something. So I was wondering what that small parameter was.
Well, it's the particle diameter divided by a characteristic length of the inhomogeneity.
So that's what I was.
Oh, that's what you meant. I'm sorry. Yeah.
So the 9 pi by 12. So those corrections are at order D, or order D.
D over some L.
Yes.
Yeah, exactly.
And then the next correction which you are hoping to do next time would be the order E.
Oh, yeah, 1 minus E maybe.
minus E, one
Yeah. Yes. I'm sorry. That you're exactly right. Okay. Anything else? Okay. So before I start talking about incline flows and inhomogeneous flows and boundary conditions, let's see what the theory predicts for a steady, homogeneous shearing flow. Simple shear. Okay? So here's a profile that I want to look at, and really what I want to indicate to you is how the energy balance works to determine the temperature. Okay, and then how we can use that temperature in the equations for the shear stress and the pressure to come out with relations that look more like rheological relations. So, all right, so here's the situation. So in this, the U prime is what I mean by prime is a derivative with respect to a coordinate perpendicular to the flow. So U prime, the shear rate, is constant, and the temperature is assumed to be uniform across the flow, as is the volume fraction. So this is what I mean by simple shearing flow. And in a simple shearing flow, the shear stress, just making use of the constitutive relations of the previous slide, so I'm doing nothing more than taking the appropriate components of this and the expression for the viscosity, and I can write then the shear stress as a function of the mass density, here I use d rather than sigma for the diameter of the sphere, I beg your pardon. This function g, t to the 1/2, and u prime. And similarly, the rate of collisional dissipation is given in terms of these quantities. Again, this d should be sigma. And finally, the thermodynamic pressure has a form that is simple. That is, this is the mass density of the flow. This is this function g, a known function of nu, and this is t. And maybe I should say that the full expression for the pressure looks like this. That is, what do I mean by full? I mean, if we're dealing with, if we're attempting to, if we want to have a dilute contribution as well as a dense contribution, that's what I mean. So this is the dense contribution here, and we're only focused attention on the dense contribution, and this is the dilute contribution here that we're ignoring. But, you know, if we didn't do the dense concentration, then the pressure relation would be something that you're probably accustomed to. The pressure is just rho times the temperature, T. Okay? But we're focused only on the dense contribution to the pressure, so it's not as familiar or so familiar. Okay. So there's these are just the constitutive relations written out, and now I want to look at the energy balance. And the energy balance has a pretty simple form. We only have the shear stress working against this, the gradient of the flow velocity normal to the flow. We don't have a divergence term here because we're homogeneous, because T itself is constant, so that the quantity in parentheses is constant. So the energy balance is this steady balance between the rate at which fluctuations are being created by collisions in the flow and the rate at which the energy of those fluctuations is being dissipated by virtue of the fact that the collisions are not elastic. Okay, so we substitute in for S, substitute in for G, and solve the resulting equation for T. So here then is an algebraic determination of the strength of the velocity fluctuations, or sometimes called the granular temperature, in terms of the shear rate. And the idea is that the temperature is quadratic in the shear rate. Okay, notice also that the value of the temperature, as the material becomes more and more elastic, as E becomes closer and closer to unity, the temperature is going up because the dissipation is decreasing, and in the limit of elastic particles there is no steady temperature. Okay, that's when we agree with the molecular gas. Okay, so the temperature is quadratic in the strain rate, so let's use that in the constitutive relation. So we'll substitute that in here. So T to the 1/2 is linear in the strain rate, so the shear stress is quadratic in the rate of strain. Okay, also let's look at that let's use that in the temperature. We substitute it in the temperature and the pressure. We substitute the temperature in the pressure relation, and the pressure relation is quadratic. Okay, so both the shear stress and the pressure are quadratic in the shear rate in this simple shearing flow. Okay, and that's an experimental observation that's been around from the time of Bagnhold, who was really the father of this kind of collisional dynamics of the shearing of particulate flows. Okay, so
So in the top line, so we prescribe u prime as constant,
yes,
and the p prime and u prime come out to be constant.
well, that is a possible solution. Yes, yes.
It's not like we prescribe all three. We prescribe one, and the remaining two are.
No, that is, if you carry out the simulation in a way that doesn't use boundaries that can introduce inhomogeneities. So the technical way of carrying out these simulations is to do it in cells that are periodically reflected. So you have effectively no boundaries in and in that case, the result is T is constant, nu is constant, and
No, I guess what I was getting confused with was when you say simple shear is defined by that, are you saying that?
well, I'd say that's the solution to
Then
the
it is
equation.
solution? Yes.
Okay.
To the,
Yeah.
balance equations.
Yes.
So why is the volume fraction affecting nu?
Why is the volume fraction affecting what?
It's not coming anywhere in the picture in terms of.
Well, it's not affecting T, right? So T is not sensitive to the volume fraction, but the volume fraction is influencing the shear stress through the function here and the pressure through the function there. It's influencing both of those through capital G. On the other hand, if we looked at the ratio of the shear stress to the pressure, there's no influence of volume fraction there. Okay, and that ratio is important for many reasons. I mean, as we found out in the lectures on the mu-I rheology, the focus of the mu-I rheology is on that ratio, and also in steady incline flow, that ratio is constant and equal to the tangent of the angle of inclination. So that ratio is important in many situations. But it's independent of nu in this dense limit. Yeah. Did I do something wrong here? Let's see. I put a nu in there. Oh, I'm sorry. That's wrong. Okay. Yeah, I guess yeah. I'm confusing what I introduced as rho s and rho. So rho s is the density of the material of the spheres, and rho is the mass per unit volume of the gas, and they're related. Okay, through nu. But thank you. You're right. Okay, so that's simple shear. But what we're interested in is flows, let's say between parallel boundary. I mean, I talked about this flow. Another flow that you can imagine, maybe in a numerical simulation, is you could do a flow between parallel boundaries. Let's say we have gravity present, and this boundary is moving with some velocity relative to this velocity. And the situation there then is that typically the exchange of momentum in collisions between particles and the exchange and dissipation of energy in the collisions between particles within the flow is different from the exchange of momentum and the transfers of energy and dissipation of energies in collisions between flow particles and the boundary particles. And as a consequence, the presence of boundaries create inhomogeneities in the flow. Okay? And so that's fine. That's of interest to us. So what we'd like to do is we'd like to be able to determine boundary conditions for the momentum transfer and the energy that would allow us to say predict the profile of the velocity and the profile of the temperature and the profile of the volume fraction. Whatever they may be. Okay, so that's where it goes. So this is an example of a parallel flow driven by top and bottom boundaries. This is the incline flow is an example of a flow. So this is influenced by gravity, but not driven by gravity. And this is driven by gravity, but we also have to understand the transfers of momentum and energy at the rigid base. And similarly here, we have to understand transfer and momentum and energy at a particle bed. Okay, so let's talk about boundary conditions. Now, the way we get boundary conditions is it's not so mysterious. We consider first the transfer of momentum, let's say maybe the transfer of the component of momentum parallel to the boundary in a collision of a flow particle with the boundary particle. So I'm assuming that boundary particles are spheres, not necessarily the same size as the spheres of the interior, maybe not necessarily the same material as the spheres of the interior. Okay, but in any case, we characterize the momentum exchange in a single collision between a flow particle and the boundary particle, and then we do some simple averaging over all possible collisions. Okay, I mean it's not so mysterious, and of course, all possible collisions. That idea is influenced by the geometry of the particle. That is, let's say a collision between this particle of the flow and this particle of the boundary there's a sheltering, let's say, of this particle by its neighboring particle, and that we take into account in carrying out the integration over the probability. We just use a Maxwellian probability distribution here too. Okay, so the result of the momentum exchange is going to depend upon how far the flow particle can penetrate between boundary particles. The deeper it can penetrate, the more effective the tangential transfer momentum. Remember, we're dealing with smooth spheres here, frictionless spheres. Okay, I mean we can generalize all this to spheres with friction. So that we're going to get more effective, excuse me. Now I'm in trouble. I can advance this. So we get more effective transfer the more deeply the flow particle, on average, can penetrate between boundary value particles. And we denote that average penetration by an angle theta that we call the bumpiness of the boundary. Okay, so boundaries with bigger theta have bigger bumpiness. And you can get bigger bumpiness in two ways. If the particles of the boundary are identical to the particles of the flow, you just separate the particles of the boundary a little bit and the flow particles can penetrate more between them. Or you make the boundary particles bigger than the flow particles at the same separation between their edges, and it becomes bumpier. Okay? And of course, if you made the wall particles smaller and smaller and smaller, pretty soon you have zero bumpiness, or something very close to zero bump. All right. So the point is, the geometry of the boundary, the roughness of the boundary, bumpiness of the boundary, is determined in terms of a single parameter, and you can do the kind of algebraic or do the geometric analysis about all kinds of sheltering here, and you can come up. All right. So here's the boundary condition then that results from looking at the exchange of momentum parallel to the boundary and perpendicular to the boundary, assuming when you're doing this that the average velocity of the flow relative to the boundary is not 0. Okay? Slip at boundaries is generic in granular flows. Okay, so those experts in fluid mechanics here have to give up the no slip condition, all right, and replace it with a slip condition. And so and that slip condition influences the tangential transfer of momentum, of course. And when you do that calculation, what results is a relationship for the ratio of shear stress to pressure that involves a function of the bumpiness that can be made explicit. That is, it's a more complicated function of this. This is an expansion. And that function and the slip velocity divided by the square root of the temperature. Maybe I should have emphasized that the dimensions of the temperature are velocity squared. Okay, I mean, it might be more natural, and in certain instances it is, to have temperature have dimensions of energy, kinetic energy. Okay, but here the temperature has dimensions of velocity squared, so that this is dimensionless. And we're going to see that part of the solution of a boundary value problem in the context of this theory is the determination of the slip velocity. Okay, so that's, I say, it's a new feature if you're accustomed to dealing with gases and liquids. Okay, so that's the balance of momentum at the boundary. And now we do the same thing for the balance of energy. You look at the change in kinetic energy of a flow particle in a collision with the boundary. You do appropriate averaging, taking into account the limitations that the geometry of the wall particles place upon the collision, and you get a relationship that equates, and I haven't really written it in maybe the appropriate way, it relates the working of the shear stress at the boundary through the slip to the creation of velocity fluctuations at the boundary and their dissipation. So the situation, what's happening at the boundary, is this.
These S and P are externally applied, or the ones in the material close to the boundary?
Well, those would be, no, they're applied by the boundary.
By the boundary on the floor.
Part of the solution is created by the flow. The boundary is fixed.
Yeah, boundary's fixed. So what's happening? So what's happening is we have a non-zero slip velocity. And maybe I missed, let's see. Okay, so we have a non-zero slip velocity. And we have a shear stress, let's say, that's related to the momentum transfer from the flow to the boundary, and equal and opposite from the boundary to the flow. And let's say a typical collision. A typical collision of a flow particle with a boundary particle, and of course this guy's moving with B, the typical collision creates a fluctuation. It scatters the particle. Okay? So attempting to move this cloud of particle past a bumpy boundary is forcing collisions between particles of the flow and the boundary and creating these fluctuations. Okay? That's Q. On the other hand, each one of these collisions involves dissipation of fluctuation energy, and that's D. Okay? So in this instance, the boundary can serve either as a source of fluctuation energy or as a sink of fluctuation energy, depending upon which of these is larger. Okay, well, so that's the story of the boundary, really. Oh, I should say that here, okay, so the new element, maybe if I learned how to use this. Okay, the new element is this guy, which is a function similar to this function that appears in the exchange of energy. Okay, and here I've permitted the coefficient of restitution in a collision between a flow particle and a wall particle to be different from the coefficient of restitution in a flow-flow collision.
Could you please comment on theta going to 0 in F? Because you are
That's a slippery boundary. We don't. I mean, there's no, in that instance, there's no shear stress. There's no
there's no pressure, it seems. Because it goes to infinity.
This goes to infinity. So you're saying, okay, well, so this is going to infinity. You say, yeah, exactly. Okay, so that's strange. So what am I saying? Well, let me say it this way. The slip velocity is also going to infinity. So I think that's the way you understand the limit. As theta goes to 0, v goes to infinity.
So F and V both going to infinity keeps the right hand side infinity. And you have S over P on the left hand side.
Ah, good point. Okay, so let's see.
Maybe in the derivation there is, it's around theta equals something.
Well, I don't know. That limit, of course we don't care about because we're interested in maintaining the transfers. Yeah. But you're right. That is we ought to be able to understand that limit. So let's see. Because P doesn't go to 0.
When theta equal to 0, how is slip velocity infinite? I mean, it is normally hitting the base, so there is no slip component.
Well, no. As theta is getting smaller and smaller, there's less and less resistance to the flow at the boundary, so that
But this is just a boundary condition regardless of gravity. It need not be an inclined plane.
that's true. This is not
I
it.
just have a horizontal channel in which I'm firing these things from some compressor, air driven something. In which case, if it is frictionless, the velocity could still well be finite.
But there's no resistance being
That's clear.
given
So
to the.
that's why I think the shear should be zero, not the pressure.
Yeah, I agree with you. Yeah, but that's not what's being said here. That's all. No, I agree.
Shear 0 would not work, right? You need shear infinity.
Well, but let's not get fixated on these smooth boundaries. Okay, so I mean, I don't recall it, but there may be a part of the calculation where clearly theta equals 0 is excluded. Okay. All right. So the point is, we've got boundary conditions. That is, for
In these boundary conditions, the base is fixed, the wall is fixed.
the wall is fixed. Yes.
Because many of the experiments, actually the walls is driving.
Well, but there's no, then the slip velocity is simply the velocity of the flow relative to the wall. Yeah.
And in those cases, sometimes I get confused between the shear of the flow and the wall and the shear applied on the wall.
Yeah, but aren't they equal and opposite?
Not an accelerating flow.
Or not in an accelerating flow? Okay. Yeah, so at the moment, I'm focused on steady flows.
I was wondering in that case which would it would be more complicated.
Okay. What time is it? How much? Pardon me?
Exactly.
Okay. So now let's consider the incline flow that I mentioned. So I've drawn it as if it appears that x and y are horizontal, but no. Gravity is at an inclination. We're going to look at a flow of a depth h, and eventually we'll relate that h to parameters of the situation of the system. And now let's see. So it's a simple one-dimensional flow with variations. It's steady, fully developed, so there's no variation along the flow, and there's only variation perpendicular to the boundary. Okay, so in that instance, there's a balance between the gradient of the pressure and gravity. And so this is an integral of the component of the linear momentum equation perpendicular to the boundary. And the combination of the tangential balance and the normal balance gives us that the ratio of the shear stress to the pressure is equal to the tangent of the angle of inclination. So this is the way that the momentum balances are satisfied in this simple situation. We have a specification of pressure as a function of the vertical coordinate, and we have the fact that the shear stress is the tangent of angle of inclination times the pressure.
That's just from the steadiness and the incline. Yes, it's not-
Steadiness and the incline. Yeah, exactly.
And we believe steadiness is possible because of gamma, because of dissipation.
The steadiness is possible because of dissipation, although that doesn't influence what I've just said about the shear stress and the pressure. That's the energy equation.
No, because I saw a component of gravity along the flow.
Yes?
That's not accelerating the flow because you have got dissipation which is taking care of the,
Well, you have the tangential resistance of the base.
yeah, the base
Yeah.
and the internal
Yes.
dissipation resistance.
Okay, so now we're going to look at the energy equation. And there's something wonderful that happens when we deal with I'm sorry, it looks like I'm dealing now, I'm calling the diameter of the particle d. There's something wonderful that happens in the energy equation, is that the equation that results from substituting everything, the constitutive relations into the energy balance and evaluating them on this simple one-dimensional flow with one dimension of variation, what results is a linear differential equation for the square root of the granular temperature. That's a miracle. The coefficients in this differential equation are not constants. They're a known function of vertical position. And the coefficient that I call k squared here then has something to do with the balance between dissipation within the flow and the creation of fluctuations due to the working of the shear stress. Okay, so that's the physics of the situation. In simple shear, we really were just focused on these two terms in the energy balance, but now we're anticipating that there are going to be variations across the flow due to the fact that the boundary interactions are different from interactions within the flow. So that's why we this term, why we retain that term. Okay, so that's the energy equation, and it looks like we're going to be able to solve that using relatively routine methods, and then if we invert the relationship between the stress, the shear stress, and the strain rate, we get an equation for the y derivative of u that we can integrate once we determine what the solution to this equation is. Okay, so first we phrase the boundary value problem. Well, I haven't said what boundary conditions I'm going to apply at the free surface. I mean, that's an important part of the problem too. But I think you'll grant me that a reasonable pair of boundary conditions is that the shear stress at the free surface vanishes and the energy flux at the free surface vanishes. So I'll impose those two boundary conditions at the free surface.
Is it a three-boundary problem? Are you trying to locate the boundary as well? Or do you know where the boundary
No, we predict where the boundary is. Yeah, we're going to predict the slip velocity, we're going to predict where the boundary is, and predict the profiles of rho, u, and t.
I
Okay.
thought you already assume a height of the layer.
Well, but I'm going to determine how the height of the layer varies with the angle of inclination.
Given some initial layered thickness, right?
Not necessarily, but you're right. I'm going to have to specify
Use
some other piece of information
either
that,
mass flow rate or something.
yeah, exactly. Yeah, you're too expert. Yeah, so that's going to be necessary to close the problem. Okay, so is it clear? So I phrased the problem, and it looks like I can proceed to get a solution. All right,
You said that the top boundary you're going to say no heat transfer,
yes,
and you're going to say no shear,
yes.
but you will need a P, right? In that equation there is a P.
Yeah, so the P also is 0. Yeah, that's a particle pressure, P.
Yes.
Yeah, you're right. So, but I've already implemented that boundary condition, if you like. Yeah, so when y is equal to h, the pressure is 0. But you're right. I've imposed that. I've said that. Okay, anything else? All right, so now the details of the solution get a little complicated, as you might expect, but so bear with me. So the solution to this equation is in terms of Bessel functions. I mean, this part of the activity you might regard as being historic. At this point, any one of you might take a look at this system of equations and implement it in MATLAB and have it solved in 30 seconds. Okay, so you certainly can do that. All right, I'm going to go through the solution. Okay, so the fact that where am I? The fact that the energy flux is 0 at y equal h means that the derivative of W, so the square root of the temperature, I sometimes refer to as the fluctuation velocity. All right, so the derivative of the fluctuation velocity is 0 at y equal h, and consequently the solution for y equals h is given in terms of these Bessel functions and this quantity k. And maybe I'll just keep reminding you of what k is. So we'll go back and forth here. K, if I know the coefficient of restitution, if I know the angle of inclination, I know what m and j are. Okay, so k depends upon coefficient of restitution, angle of inclination. I can measure coefficient of restitution in experiments in collisions between particles. I know what this is. So k is known. Okay, so that's fine. So I've got a solution, but that solution is parameterized in terms of the value of the fluctuation energy at the base at y equals 0. Okay, that's fine. And now I'm going to use the boundary condition. I'm going to use this boundary condition. So in this flow, this ratio is equal to the tangent of the angle of inclination. So that's known. Okay, so I'm going to solve for this relation for the slip velocity. So this is solved for the slip velocity, and that involves the square root of temperature at y equals 0. So we got that parameter appearing in two places here. And then I use this knowledge to solve this equation. Just make an integral of this equation, making use of the condition that at y equals 0, the flow velocity is equal to the slip velocity, and making use of this form of the solution in this integral. Okay, so if you like, I've almost completed the solution. So what parts are missing? I've got to say something about the value of the fluctuation velocity at the rigid bed, and what else? And I've got to say something about nu. I've got to find out how to determine the variation of volume fraction. So I'm getting close. So I'm imposing another condition on the derivative of the fluctuation velocity now at the rigid bed, and this condition is the version of this quantity of this relationship when I use the constitutive relation for Q, the constitutive relation for S, and this relation for D at the boundary. And when I do that, that gives me a value of the derivative of W in terms of the value of W itself, and these quantities, which, if I know the bumpiness of the boundary, are known quantities. So this is a specification. So this is a specification of the derivative of W in terms of W itself at the boundary. Now, I should say that both this boundary condition and let's see. Well, the boundary condition and K has to do really with the relative magnitudes of the two terms that appear here. Okay, if, for example, this quantity in brackets is negative, then K is imaginary, and another type of Bessel functions are the solution. Okay, so we have various types of solutions that are associated with various relative sizes of the terms that appear in these brackets. Okay, so I say that, that's good. So let's see. So I implement this boundary condition, and that gives me a condition that relates these two different Bessel functions with this quantity having to do with the energetics of the boundary, and K having to do with the energetics of the interior. And I can, in principle, solve this relation to determine the thickness of the flow in terms of particle diameters as a function only of the angle of inclination. Okay, so one thing that comes from this analysis is that at a given angle of inclination, there is only one thickness of this dense flow that is possible. Okay, so keep that in mind. And we can determine what that thickness is. So this is the determination of the thickness that I promised you in terms of the angle of inclination. Okay, and then you have to work a little bit harder to get the volume fraction, and the volume fraction then comes from the pressure relation, and using essentially the information in these two solutions. Capital U is the value of U at the top of the flow. So that appears there, and we know something about this. Well, we still don't know W0, okay? But here, in order to determine what the volume fraction is, I have to impose this additional condition. And the kinds of additional conditions that are more physical are you either specify the total volume flow rate in the incline flow, or you specify the what's sometimes called the mass holdup, the amount of mass per unit area of the base. Okay, but for my personal convenience, what I'm going to assume is specified is the velocity at the top of the flow. Okay, and they're all equivalent. Okay, if I do that, then I can, and then let's see. Then everything in this thing is known. Everything is known, and that gives me G as a function of nu. And when I have G as a function of nu, I can invert the relationship between nu and G and determine nu. And then finally, I can get W0 in terms of the value of nu at the base. Okay, so it's complicated, but you know, it's pretty explicit. It's done in terms of elementary functions. And you've got, at least in principle, the way that all the variety of solutions depend upon the various parameters. Okay? And the reason I'm saying that is if you solved it numerically, you'd have to solve it for each set of parameters. So although I said it took 30 seconds to solve one case, it might take longer to solve 1,000 cases. Okay. Yes?
How realistic is that assumption that for a given thickness you have exactly?
It's not an assumption. It's a result of the calculation. Okay? We're going to see that it's wrong. Okay? Don't worry.
Thank you.
Don't worry. Well, I'm not going to, I would say it's wrong for the dense flows that are realistic. That is, on Earth, incline flows typically have volume fractions that exceed 50%. Okay, that's what I mean about realistic flows. The theory and the consequences of it, I believe, are true in the range between 30% and 49%. And that's something you might check.
So in fact, I have checked that. And in terms like if I do a flow of inclined flow exactly sticking to your assumptions of smooth particles, restriction coefficient pretty close to 1.88 to be precise.
Dense?
Yes. And so your repacking friction is around 0.5. So I'm exactly at your bottom.
Yeah, better if you were below it, but go ahead.
Yes. Then so the range of angle is of course pretty narrow. So it's like, I get a flow only from 14 to 14 degree and 15
Okay,
degree.
yeah.
It's pretty
Yeah,
narrow.
yeah, I understand.
So it's there, but so I was just wondering, do you mean that or alternatively you're saying a slight change in theta essentially leads to slight change in h?
No, yes, exactly. But the stronger thing is I'm saying there's only one thickness for a given angle of inclination, no matter how much material you're trying to put down there. Okay, and the way that it accommodates more material is by changing the volume fraction of the flow.
That's correct, because for hair thickness, I didn't get any steady state. So in that sense,
Okay, but I believe I've seen numerical simulations that provide some support to this in this range of angles of inclination.
yeah, I think I'm saying the same thing, except that the range is very narrow.
Yeah, I'm not saying, okay, yeah.
The range is basically
No, but I agree. This is a very striking result. Okay. Okay, so what else? All right, so now I'm going to show you profiles of velocity and fluctuation velocity, square root of granular temperature, and volume fraction. I have to check the time. Okay. All right, so here's what results. So here are parameters. So what I'm assuming, I should, so I'm assuming a very energetic system. And that's why I'm getting solutions, perhaps, that you wouldn't get for a more realistic system. So I'm assuming that my coefficient of restitution 0.9. So the bumpiness of the boundary is pi over 5.5. I think I said someplace earlier that if I have a hexagonal close packing of spheres on the boundary, the bumpiness is pi over 6. So this is slightly more bumpy than a hexagonal close packing of spheres on the boundary. And let's see. And I have a single angle of inclination and several values of the velocity at the top of the flow. Okay? And here are the velocity profiles. They're not crazy. Here is the predicted slip associated with each one of these profiles. So we're predicting the slip velocity at the bed. And here are the temperature profiles. The temperature is greatest at the nearest the bed. There's slip at the bed. Consequently, there's a lot of production of fluctuations at the bed because there's not much dissipation at the bed, so that the energy is being put in to the fluctuations of the flow by the slip velocity at the bed, and consequently the temperature is highest at the bed. Okay, and then here are profiles of volume fraction. For the same situation, let's see, for the single, okay, so here I'm doing a single, I'm holding the velocity of the flow constant at the top, and I'm doing various angles of inclination. Okay, and notice that I'm exceeding the volume fractions at which I was hoping to work. I was hoping to be within 0.49, but that's okay. I want to push the theory as far as I can. So I'm pushing the theory up to where the greatest volume fraction I'm looking at is 0.6. Now, the important thing to observe about these volume fraction profiles is as the inclination becomes greater, the volume fractions associated with the flow also become greater. Okay? And that, it turns out, is a feature that is not characteristic of the more dense flows. Okay? So I think I'm going to stop there, and then what I'll do in the next lecture is we'll test these predictions against the results of numerical simulations of incline flows and see to what extent they fail or not, and in instances where they fail, we'll try to propose an extension of the kinetic theory that will be predictive. Thank you.